My name is John Hodgson. I am an application performance management subject matter expert, except I can't say it. I've been doing this for about 13 years, specifically in APM. I've been doing performance in some form or another for about 20. I work for Riverbed. I'm in the office of the CTO. And we are largely known as being a networking company. We do WAN optimization. But we have a very profitable part of our business called Steel Central, which is around performance management. And so we have the ability to look at the performance of applications by using network packets, code traces, and user experience monitoring. And this presentation is about lessons learned in the field, where we've seen customers that are using the wrong techniques that wind up not being able to solve very critical problems or not effectively. So the goal of this is going to be a non-marketing presentation. My marketing people sent me 2 slides, of which I used 1 line from one of them. So it's all technical, it's all practical, and you don't have to have our tools to do this, but it might help. So the goal of this is for me to help you navigate these common landmines that I see. There are sort of these particular issues that customers keep tripping on, and hopefully when you come out of this at the other end, you'll have some skills that will help you solve real-world issues. So the first challenge I'm going to make to you is to think logically about your environment and architecture, not physically. So with the new world of hybrid cloud, microservices, all of this sort of virtualization, it becomes very difficult to make sense of our world. Web scale is something we all strive for. We want to have these big applications that we can brag about and make lots of money on, but they become a nightmare to manage. Elasticity and transience makes it also very difficult, because if you're trying to monitor the health of something and it goes down and then comes up in another identity somewhere else, it's very difficult to make sense of all this. And of course, it's all abstracted, right? We don't really know where our servers are. We don't know physically where they're located. So, if they could be in different states, that could add latency and so on. And the questions that you would ask as an app owner or a troubleshooter, right, which is, what is my architecture? Typically, we want to know how are the pieces of my environment connected together so that you can understand your dependencies. Now, in the old days, coming from the systems management world, dependency mapping was about understanding if I move this server or I decommission this server, what will it impact? But the world that we live in now, we're sharing things like code, we're sharing microservices, we're sharing libraries. So dependencies have to be thought of in a much more microscopic level. If I change this method, what are all the things in the business that could be affected by it? It might not just be my transaction in my app, it could be other apps in our enterprise that are sharing some common library. And from a troubleshooting perspective, what are the things I should fix or focus on to basically have the most impact to the bottom line of the business? So this isn't a game anymore of just simply reducing seconds. It's about how do we maximize the profitability of an application that we're part of, or minimize the cost associated with using it. So this is an example of a physical application map. This comes from our APM product called App Internals. And this is one of your traditional maps, which shows you the physical servers, the JVMs or CLRs inside of them, and how things are talking. Now, you may see ones like this for individual transactions. You may see aggregated versions, which represent the whole environment. But this is just 2 app servers. There's 2 larger boxes and some downstream things. This is actually quite complicated looking, and it's simple. Now, you imagine you take this app and you scale it out with elasticity, and over the course of the day, you may have hundreds of these instances coming up and going down. This map could actually get quite complicated. And here's another example, which again, a simple application in QA, not even the production scale version, becomes quite complicated. And it's harder to read, and what kind of value do you get from it? And this, which is the best or worst for last, depending on how you think about it, this map is an example from one of our largest customers. Very well-known customer, and you can't even read it. Here's a zoom into a part of it, and you still can't read it. The complexity is just mind-boggling. So it's great when APM vendors show you that they can do all of this mapping and connect the dots, but my question would be, if you have this sort of problem where you need visibility the most, are you going to be able to really glean any information from that? So the idea is to now look at things logically. So we have introduced something called performance graph. Graph in our world is not about a chart. Now, a lot of people think that's what graph means. But we're talking about mathematical and statistical graph theory, about the logical modeling of relationships between things. So companies like LinkedIn and Facebook use that methodology for applications like social graph, knowing you're n levels away from somebody on LinkedIn. So we've chosen to take that approach and apply it to performance management. So this is a logical representation of where you're spending the most delays. On the left-hand side, you have the types of transactions people are doing. And on the right, you have things like methods and sequels, the actionable things that are causing delay. So this helps you, regardless of your physical scale, regardless of the elasticity or transience of the nodes, be able to know, here's a certain thing I need to improve, and here's why. And there's various pivots and so on of it, but the idea here is that we built this to overcome the challenges that are really prevalent in physical mapping. Just about every APM vendor in the space, if you search for their maps and you look at them, they look very impressive, but then when you think about it, you go, I don't know how to interpret that at all. And we decided to change that. So this is an example of the performance graph in action. On the right-hand side, we have a 5-minute window period. Again, this is real-world data where there was clearly a very visible spike. And on the left, it's the previous hour. And so we can see the change in the structure. We can see on the left that a particular transaction became more dominant with regards to the total amount of delay experienced by end users. And on the right-hand side, we see a very specific method that pops up out of the noise that is now different. So on the left, we don't see it. On the right, we do. And that helps our customers look very clearly and say, OK, I need to target that. And also, it's tabulating the amount of delay. So the scale on the left-hand side is 30 minutes of processing time. But when they had this queuing issue, there was 168 hours of processing time in that little top window over the course of a 5-minute time period because of massive scale and massive queuing of tens or hundreds of thousands of transactions. So the whole idea here is that when you take a logical approach, you can step back, you can get more actionable information on solving problems. So the next challenge is to think holistically and really try to solve overarching issues. The world quite often does this, why is the slowest thing slow type of troubleshooting. I had a customer, they're a very large financial services company. They have banking, loans, mortgages, things like that. You probably have their credit cards in your pocket. And they have 30 tier 1 applications, their main types of apps. Those are thousands of different types of transactions across those different applications. And one of their pages, their account details page, when you first logged in, was extremely slow. And they were seeing response times, in the several seconds, and they were trying to figure that out. So for months, with other APM tools, they had been trying to solve it. They'd been identifying what were the slowest transactions, and then identifying what are the methods in SQL that are making those slowest transactions slow, yet the problem persisted. So this is that concept you'll hear me say, why is the slowest thing slow? That's not the way we should be doing APM. We have to step back. So what I did is by using our approach to things, we said, let's analyze all transactions. We have big data approach. We can collect billions of things in microscopic detail. Let's look at all of them and figure out what are the common things that are causing slowness. What is the overall slowest method? So instead of identifying the things that took 500 milliseconds and so on, we identified, you'll see, a interesting dominator. Now, why this works is that pie chart at the bottom, imagine that as a particular type of transaction, log in, add to cart, whatever. And we see the pie chart of delays. Method A is the slowest thing with 80% delay, and Z is 20. Now here's another transaction where method B is the dominator. So if you want to fix the top one, you have to optimize A. You want to fix the bottom one, you have to optimize B. If you want to fix the application comprised of those two, well now A and B share that 80% and now they're 40%. Now this one still doesn't look that impressive, but if we go to 4 different types of transactions, they're all actually equal to that little guy Z. And as we add more and more complexity to my applications with more and more different types of transactions, which each have their own reasons for delay, it turns out that these individual 80% constituents, when they roll up, they're actually not that big a deal. And the little number 2 guy, Z, because he is common across them, becomes the dominator. And if you then roll this up to the enterprise, all of a sudden, all those little things that matter don't matter so much in the big picture. Now, that's not to say you shouldn't target individual things to fix. Clearly, you're going to do that. But these are problems that I see existing in my largest customers where there are lingering issues that are accumulating thousands upon thousands of hours of delay a day, and nobody fixes them because they don't show up in the top 10 list of slow methods. Right? So this large-scale, holistic approach is critical to really getting some of these problems out of your application. So the benefits that they saw by taking this approach was they targeted this little 53 millisecond method. It was a logging method. They were trying to do their own logging. That's what APM was for, but they had this in there since before that. The average response time of their transactions were about 1.1 second before they optimized, And once they optimized this one thing, which had mutex locking, the response time went down to 62 milliseconds on average, very consistently. And that was a 95% improvement in response time. It affected 7 million transactions a day and accumulated to over 2,000 hours of savings per day because of death by 1,000 paper cuts every time this little stupid thing ran. Because it ran maybe potentially thousands of times per individual URL. After this, they had an after-action report where the management wanted to understand more about this. The developer said, we knew that this could be improved, we just didn't realize what a big deal that was. And I've run into this more times than you can imagine. I'll show something to customers and they'll say, no, that's a red herring. But then when we show them the aggregate impact of it, they go, oh my God, I didn't know it was that big a deal, right? Management said, how long has it been like this? It had been like that forever. This was a core functionality they've run for years upon years. And every day they had been wasting thousands of hours because of this code. And lastly, what else uses it? And this now goes into our microservices and shared environments. Everything. This was a core library for this organization. This wasn't just the account details page. It wasn't just the banking app, but it was mortgages and loans and equity management and all this other stuff. So if we think of this, there were thousands of transactions that were actually improved by this once they rolled out that code to all of those different apps. It accumulated to probably tens, if not hundreds of millions of improved transactions per day, all by fixing one stupid little 53 millisecond method. So I cannot stress enough that you need to take a step back. So the trick is to not just look at your transactions in the micro. Let's drill into the call stack of this one slow anomaly. Let's see what are the things that are affecting the environment as a whole. So here's just an example of the complexity as we drill down. Global enterprise, and again, that's that physical map you can't read. Different lines of business, I've shown 3 of the 34. Then I've got the transactions of which they have their own complexity. And again, that concept I showed earlier of the rolling up of the delays is what ultimately, this is why it happens. So this is math, right? This isn't just theory or a presumption. I see this continually where little things like this make a big difference. So now the big challenge is to really leverage true big data APM. And you'll see true is highlighted, is italicized, and I'll explain why. Actually, steps 1 and 2 are possible because of this, but I didn't want to lead with the technology. I want to lead with the benefit. So the idea here, let's talk about what we're really trying to achieve with APM. We're trying to get as close to pure visibility of end-user transactions as possible. So the legend in the corner is just sources of delay. Red means database and so on, but don't worry about that. At the top, I have a user clicks on a web page, and there's some URL that has parameters like do equals this, x equals 2, and so on. And then that's going to have to traverse over a WAN, go into some container or host, and hit a JVM, and then it spawns maybe a JSP. Again, those parameters are passed. Then methods get executed, and it calls a .NET CLR, and the more parameters are passed and changed. And then this goes to another host, and then that makes a SQL call. It goes out somewhere. Response comes back. There's some more processing, a remote call somewhere, and then it comes back. We've got a loop, and then we're done, right? We get our payload, we get our images, and the page paints. This is one page. This is one out of millions and millions that a successful website will have every single day. Multi-tier complexity, lots of code involved. The parameters, the individual details, that this is a foo equals this versus a foo equals that. This is really critical. And you'll see why I make a big deal about these parameters, because you could roll this up and get stats on foo.jsp, but maybe there's something specific about when a certain parameter is passed. Or you can get aggregated stats of select this from that where ... but maybe it's different when xy equals 8 versus xy equals 12. So you want to be able to roll up your data, but you want to retain the details so that you can capitalize on that and leverage it in other ways later. So imagine you have millions of these per day. I only drew maybe 30 or whatever. And now you have to provide stats on it. What typically happens is APM tools will watch these transactions as they pass, and they will extract information about them. They'll say, here are the top URLs in there. C.JSP happened 134 times. Here's the average response time, so on and so forth. Here's the data about the SQL visible. Here's your top slowest SQL. And so they're doing big data APM. They're collecting all this data, but then they throw away the source data because you can't possibly keep all that. It's just too big, right? So this is useful. Nice compact metadata of the large information. But what if you need to ask a more complicated question? What if you need to say, for all the JSP pages that contain a specific SQL within a certain response time range, why are those collectively slow? Well, it's not technically possible to do that from the rolled up data. Because this at the top is what's called microdata. If you look at how censuses are taken, when someone fills out an individual respondent sheet, that is microdata. It's about me, John Hodgson. But then it gets rolled up into macro data, which is, I am within this age range, and I am this education level, this income level, and so on. Now that's useful for high-level summaries, but if you want to get that in the middle, you have to extract that from the microdata. It's the only way to get that ad hoc analysis. So it's critical that your tools don't throw away the detail after they've tabulated the pretty things that drive the dashboards, because you'll never be able to answer that, what is the overall arching thing that's slow, or is a particular remote web service causing delay? You're not going to be able to do that unless you retain the microdata. So here's this in action. Here's a screenshot from our App Internals product. This is the, sort of the easy-to-use UI. It's a list of my top transaction types. I've got a securities transaction with 75,000 executions. I highlight a row. I can drill down, get a pie chart of the methods that are causing the most slowness or SQL. I can get geography information about what states or countries transactions are coming from. And as a million little line charts and views that you can pivot this upon that you'd ever think you'd want. This is great. This is what all APM tools do. But now, what if there's something about those 79,000 transactions I need to do something more specific in? Where do I go next? So I always say, and this is an issue that I see where customers will often say that other tools are like our tool because they look at all transactions, so do we. We say 79,000 transactions, so does their UI. The question is, can you drill in and recover those 79,000 transactions? Can you see the exact pattern that they took and see the subtleties in their behavior? Can you drill down into each one of those and for every one of those 79,000 see what map, where did it flow? See the call stack of exactly how it took. So with 79,000 transactions, I've got 79,000 different maps. I've got 79,000 different call stacks and so on. And I've got all that metadata. So the foo equals this and xy equals 12, I know what that is. I know my bind variables. So that allows me to then do really advanced analysis to say, for all the ones where this bind variable equaled x, let's do an analysis on that, right? This is not possible if the microdata is discarded. Here are the cool things that I can do. So that was the sort of the dashboard view. This is now the techie drill down, I want to get into the weeds view. Big data search, where all of those facets, where SQL equals X, or user IP equals Y, or username equals this, or whatever. There's hundreds of facets. I could search like I would with Google and say, for all the securities transactions above 15 seconds where SQL was get off token, I can find the subset population of that, 600 transactions, and then do some sort of aggregated analysis to understand why that's important. So it's hard to appreciate why this is so valuable if you've never used it, but with other customers, like for example, I worked with a large bank in New York, and all of their applications were using a shared remote web service. And they would identify it on individual transactions, but that remote team had already said, no, we're fine, it wasn't us, and they sort of dismissed it. But what we were able to say is, show me all the transactions, regardless of what they are, that call that web service, and we saw this crazy sawtooth pattern. And then we put an exclamation mark in front of the query, meaning not. Show me all the ones that don't use that web service, and the problem behavior went away. So that was the thing that proved over hundreds of thousands of transactions that yes, remote dependency, other team, you are breaking us, and you need to fix your stuff, right? So this is going to help you figure that out. So to help you make sense of whether or not you can do this, I want to talk about conflation. This is a term, right? When it's a practice of treating two distinct concepts if they're one. And often when conflation is used, there's misunderstandings and misinterpretations. Now this may be a tool of deception by information providers. And I'm from a software company, I'm a vendor, and this is something you always have to worry about when you're talking to a guy like me, right? Now I always try to be honest personally, but whenever you deal with any vendor, they're going to potentially do this. It also may unwittingly occur. You may bring this upon yourself by simply making assumptions and thinking that two things are connected when they're not. So it is important to make sure that you really use a very educated lens when trying to determine exactly what you're dealing with. So here's a conflation example on the capabilities of a vehicle manufacturer. So you could send out a request for information to them and say, do you have two-wheeled vehicles? Yes. Ones that go from 0 to 60 in 2 seconds? Sure. Cargo capacity of 10,000 pounds, 8 people can seat, a sunroof. Yes, they do it all. Those are ors, they're not ands. And so for a vendor to be able to say, I can capture all transactions all the time, yes. I capture transactions down to method level detail. Yes. I capture parameters. Yes. Production? No. Can't do it at that volume. Oh, all transactions and all details? No, right? So this is where the devil in the details is of whether or not you're going to be able to achieve some of these goals. So how big is your big data? This is just a scorecard to help you sort of figure out, was the microdata retained? Do I have all my URLs with their exact parameters? Do I have my SQL statements with their bind variables? Do I have the raw packets or just a roll-up of the URLs that traverse those packets? The roll-ups, the macro data is useful for detecting issues, but you need the microdata to effectively solve those issues and diagnose. So these slides will be available shortly after the show, and I just challenge you to look at what you've got or tools that you're going to buy and see whether or not there are ands to their statements or ors, and that's really, really critical. And I'm making a big deal of this because I can't tell you how many times I've worked with customers and they say, I've got a tool that's just like yours. Okay, why are you talking to me? Well, we've got problems, we haven't solved them. Okay, but if they're exactly the same as me, what can I do differently? Well, these are the reasons why we wind up solving issues that other people can't. And did I mention big? So that is from real world customer, 3.7 billion transactions in full detail, multiple tiers, down to the method level with bind variables, and I can analyze that over weeks of periods for hundreds of thousands at once and find out this method, that parameter, whatever it happens to be. So again, devil in the details. So now this is just a more open-ended concept of not settling for inadequate data. And this doesn't just apply to APM, it applies to everything. Here's a security scenario, and we've got CCTV cameras. And we've got two frames, start and a finish. There's no difference, right? There's just cars in a parking lot. From this view, nothing happened, nothing to investigate. So if this is your frame rate, that's what you're able to see. If you improve the frame rate, something suspicious happens, right? There's a guy peeking in a window. Might be nothing, might be checking his hair, who knows? We improve the frame rate more, I know who he is, I could see he didn't have a backpack in the middle, and he does now, and the door's open. Gotcha. Quality of data is critical when you're monitoring things. If it's too coarse, better not to have it at all. You don't even know you've got an issue. You can't solve a problem if you can't even see the problem. So here's a real-world example. Data often gets, so let's forget transactional data. Let's say you're monitoring CPU, environmental metrics. Here is data from our tool, which is in 1 second data. So that is a chart of 15 minutes, and there are 5 1-second duration spikes. We see every single one of those. Now, had we rolled that data up for whatever reason, which we don't, but if we did, we would still have them. They would just be deflated because we saw them to begin with. We'll just average them in with their adjacent 14 samples. Now, other tools tend to have much more coarse sampling. So 15 seconds is what I call the best of the rest. They tend to be around there. Some are in the minute range and so on. So statistically, there's a 71% chance they won't catch any of them. There's a 7% chance they'll catch one of those spikes and at least know that it happened. And this is where it's amazing. It's a 1 in 759,000 chance that they will catch all 5. Because this is that Monte Carlo, rolling the dice, except it's a 15-sided dice and there's 5 of them and they all have to hit the exact same number, right? It is mind-bogglingly complicated. I cannot tell you how many times customers have tools and they say, everything looks fine. Well, it's because you're missing it, right? It's broken under the covers, but you're not seeing it. So really, really be critical of the quality of the data that you're capturing, as well as how you're retaining it. So that security example was 25 seconds. Now let's talk about a smaller window of time. I'm going to show you something. Pay attention. It's going to last for less than a half a second. What did you see? Lightning. Can you describe it in any greater detail? Probably not. That was 300 milliseconds in real time. So now let's look at it when captured at 9,000 frames per second. We have a cloud-to-ground event that occurs, and then 3 simultaneous ground-to-cloud bolts that come up because it's made a circuit under the earth. And it's still going. We didn't see that in the first example. It went by too quickly. We didn't capture it enough fidelity. So when your APM approach is sampling transactions, it is taking every nth one, or it's rolling up that data. It's all the difference between seeing lightning and then being able to have a long conversation on what it was, right? Obviously, from a scientific perspective, we probably didn't know that lightning did that until we could capture things at 9,000 frames per second. So we talked about needing really good data. Now, I'm going to turn the responsibility onto you, which is bewaring the flaw of averages and how you access your data, how do you query the data. So the flaw of averages, here's a river or a lake, and there's a dock with a sign that says the average depth is 3 feet. So I would say everybody in this room should be able to get off that dock, walk out, no problem. However, it's about 6 inches deep, and there's this huge pit in the middle, and this poor statistician has now drowned. Right? So the average state of his life is probably alive, but the maximum, the minimum is 0, and he's dead. Now, so this comes from the Flaw of Averages book by Sam Savage. It's a wonderful book that shows how in many, many different businesses, doing the right sort of roll-ups on data really breaks. But it's not just a funny concept. We see this all the time where people are missing things because of averaging. So let's think of something in our world, right? I'm sure we all get asked, what's the response time of some critical part of the application? What's the response time of my page.aspx? So here's a sample log. There's 10,000 executions of the exact same page, yet there's response times between 1 second and 60 seconds. The question itself is ludicrous. What is the response time? There's 10,000 or more answers to that question, one for every individual request and one for different subsets. And I had a customer tell me one time, excuse my French, but F your averages, right? If I'm a guy who's the 60-second one, I hate you. Now, I'm not on average in love with you. I don't want to use the website, right? So we really want to make everybody happy. So management wants the roll-up number. 15 seconds is the answer. It doesn't tell you anything. So we'll rely on line charts, which will roll it out, 10,000 samples, 240 answers. We could see the maximum is only about 25, not so bad, okay? Worse in the middle than in the beginning. But again, not all charts are created equal, right? At a higher granularity, we actually see that there's even more significant spikes, more thrashiness across the day. And if I roll this down to 5 second or 1 second, you would see even more prominent things standing out. Those are all still roll-ups. Even a second is a roll-up. But what is the truth is the actual big data, is being able to look at all 10,000 things. This is exactly what happened. This is the pattern. And we can glean very interesting things from this data. We'll speak to you. So we not only know why the response time is what it was, but we know, or what it was, we know that this one was slow because of method B, that was SQL X, this was method D, everyone's got a map, everyone's got a call tree. We're going to be able to make much better interpretations of this. And with the microdata, I can do things like saying, let's exclude all of the come on, clicker. There we go. Let's exclude everything that didn't have an exception in it. So now we're left with the gray guys in the front are the ones that did have errors. Okay? We see bands appear. There's these new magical patterns that are appearing out of the noise. That band was slow because of a web service timeout. And you'll start seeing these. You'll see like, why is that band at exactly 60 seconds or 30 seconds or 90, these very human numbers? Or multiples of 2, you'll see, 1024, because it's a, connection pool has exceeded, right? This one is slow because of a database timeout. This is slow because of an authentication. And these were failures before the code actually even ran, some low-level failure. Just like there's not one answer to what is the response time, there's not necessarily one answer as to what do I need to fix. Here we've got multiple issues. You could peel back the onion, or you can just solve the whole thing at once. And if you were sampling, you may not even have known about the initialization failures because they're not the top slowest, right? It's the opposite. It's because it's so fast it's broken. So that's why all the data is critical. And just to show this isn't purely academic, these are real-world scatter charts from real-world customers. The horizontal lines tend to be some sort of timeout. The verticals tend to be bursts after a stall. The diagonals in one direction are client-side queuing, in the other direction, server-side queuing. And then there are these combinational patterns, right, of sawtooths under sawtooths. You will never see this with line data, even if it's high definition. If you have never seen charts that look like this, you have never had an accurate impression of the performance of your application. So this is really critical to strive to get this sort of visibility, because this is the truth. This isn't rolled up. This isn't any sort of interpretation. It's actually what happened. So the last challenge is second to last, is bewaring performance phantoms. So I gave a whole talk on this. There'll be a little short link on this at the bottom. So performance phantoms, that's my term, about things that appear to be a problem, but are actually symptoms of some other problem. Hence, it's a phantom. You try to chase it, it causes you dread, but you can never grab it, right? And it keeps you up at night. So phantoms are all about consistency and inconsistency. If I look at this subset of the population, and for thousands of transactions, the overall delay is method C, it's a pretty good chance if I fix C, I'll fix all of those. And I can double check with the individuals and say, yeah, they're all C2. There's no variance. This is a real problem. This is, my finding of method C is a real root cause, and if I solve it, it's going to make a difference. But let's say I do the why is the slowest thing slow, right? I sample the top n transactions, or I trigger the ones that are above x seconds. Well, there's not an overall dominator. Okay, so what do I fix? I can look at individual ones, maybe the ones that popped up on my list, and for 7 different transactions, I've got 7 different reasons for delay. This is a dead giveaway that you've got a performance phantom. That their slowness is because of some shared reason. There's some shared dependency. It could be infrastructural, something to do like with the, running out of CPU. It could be something downstream like a shared web service, whatever it happens to be. So these you have to attack very differently. You have to find what's common between them in order to solve the problem. So to consider this, let's look at the ecosystem of the application. Your code runs in a JVM. It's got its own resources like heap that it's dependent on. Those JVMs are processes that run on an operating system. In this case, they're related because they're in the same box. So the CPU and memory shared in the box will potentially impact those two. Now, if they're separated, okay, they're isolated, but not if they're VMs or containers, because they might run on the same hypervisor, which now has a dependency on those physical resources. Anything at the bottom that causes that saturates is going to bubble up that chain. So let's look at an example of a phantom. And again, that short link at the bottom, there's a whole presentation on lots of examples of this. So here we have a JVM. I've got 5 different threads running 5 different methods in a loop. The top thread A is a little fast method over and over and over again, always the same response time. Thread 5 has method E, which is slower, but same loop. And the bottom green line is the garbage collection state. Is a GC occurring? Is it not occurring? So it's not. Everything's running fine, and then GC occurs. Every method that happens to be coincidentally running gets its response time extended by the length of that GC. They all increase by the same absolute amount of the length of that GC when the world stops. And then when they complete, we look and we say, from a relative perspective, A, which was very fast, now actually has an 11x increase, and E, only 3x. So you're going to look at this and say, we just had a slowdown, I see a spike in response time, method A bubbles to the top, and we all obsess over trying to fix method A. Method A is not the problem, it's a symptom. So the fact that multiple types of transactions and multiple methods within those all had simultaneous response time, that inconsistency is the indicator of the phantom. If all of the dots were method A, then we'd know to blame method A for real. And this isn't just something that may happen with garbage collection. Let's say you've got a VM, when it gets overcommitted, so you could look at something like CPU latency is an OS metric, or you could look at the hypervisor like something like ready. But if the VM gets paused, and normally you're not going to see a multi-second pause, it's lots of little sub-pauses. But when that happens, it's going to pause the whole JVM, which in turn is going to pause all of those threads. So you'll be chasing slow code. It's not the code at all. It is your virtualization environment. So this is really critical to be able to work with your virtualization teams and say, do I have dedicated resources, right? I want CPU cycles for my app, regardless of what anybody else on the box needs. If I'm not using them, don't care. They're mine, right? So it's really critical that mission-critical apps are not going to be impacted by this. And the same thing is true as you go into the cloud. Lower tiers of cloud service are going to be provisioned much more aggressively, and there's a greater chance of these micro pauses happening in your code. When you pay for the larger tiers where you're getting closer to being dedicated, the likelihood of this is less and less. But we see this all the time in cloud. We'll see this bursts in response time, and the sheer fact that there's not a consistent reason points to the virtualization environment. And these are ways that you can find that. So again, those top things are symptom, bottom is the root cause. Don't chase symptoms, right? We have a technology called TruePlot, which tells the story. Now, it may look like it's just a scatter plot, right? What's exciting about that? But the faceted coloring of it, based on the microdata, allows us to see these patterns. So we may see that there's no, so for example, there's a consistency in this 1 5-second response time. It's related to the securities transaction. This is a true issue that we can solve by chasing that. But this burst here, a little tough to see on this projector, there are multiple little dots in that vertical line. This, because of the lack of consistency, is a phantom. And we'll see issues like that as well. Like there may be a response time issue with securities. When we switch to a server-centric view, we might see that only one color is related to it because only one server is exhibiting the issue. If we see multiple servers involved, then it's not actually about the hardware itself. It's about either something common about how the code runs or something downstream which they all share. So again, that concept is really critical in finding the real problems. So lastly is being relevant. And really about being business relevant. The reason we have APM at all, the reason why we care about performance is we want to keep our customers happy so we ultimately make some sort of revenue from them, right? That's why we're all here. I mean, maybe there may be some altruistic people in the audience, but more than likely it's capitalist. And we want to actually change the way APM is done where we're not trying to optimize things and rank them based on their impact of seconds, but really based on their impact to the dollars of the business. So here's a performance graph for a set of transactions, and I've highlighted the database to show that it is just this drop in the ocean of delay. I would not even think about asking the DBA to optimize anything because from a total seconds perspective, I'm not spending a lot of time in database. But with our performance graph, we can apply a financial impact to the top-end transactions and carry that downstream across tiers into individual downstream methods in SQL and actually understand the cost of a microsecond in a particular SQL statement. So here, all of a sudden, database does become a significant contributor to delay. There's a specific SQL statement that the tooltip says is related to $170,000 of revenue. Now, this could be based on slow time. It could be based on the cost of who's using it. Maybe a certain transaction is used by the executives, or another one is used by interns. So clearly, the financial cost is going to be different. This is going to make all the difference in making sure you fix the thing that matters, not just to the top slowest things, but to the bottom line. If you do take this sort of approach, you actually become not just a necessary evil in maintaining an application, but you can actually be a strategic part of the business's plan in figuring out how to either optimize profits or reduce costs. Right? And we have customers who are using this to say, insurance company, an auto quote is more profitable to us than a home quote. What users are doing the most auto quotes? What are holding that population up? Let's optimize that so they can do more auto quotes and we can all make a lot more money and a lot more profit, right? So really want to start thinking about your triage about how it impacts the business in dollars as opposed to simply seconds. So think logically, not physically, critical in our container world. Focus on overarching issues. Little things can sometimes have big impacts. You want true big data, the microdata, retained in detail. You want good sampling. You want to make sure that you can see something as accurately as possible so you don't misinterpret the events. Flaw of averages, don't drown, right? Don't chase symptoms. Watch that video that I talked about to learn more about that. And think financially. If you do this, any one of these, hopefully you'll have a different approach to how you go back and you troubleshoot your individual apps. I'll be here today and tomorrow. If you guys want to come chat academically about stuff, I'd be happy to. You can find me on Twitter, and I'd love to see how these sort of methodologies can help you guys in the real world. So hopefully I did what I said. I helped you navigate all those traps. And we have a live trial for this for free if you want to actually use our version of this at appinternals.com. So thank you, and I hope you have a great rest of the conference.